Welcome to another CO2 Monday with Trevor. I'm your host, Trevor Matthews, and today I'm super excited about this conversation because I got a really knowledgeable and an expert who has traveled the world learning about CO2 refrigeration, Benoit Grodier. And I'm super excited about this because Ben has been working with Simco Refrigeration, who's one of our largest industrial contractors in Canada, maybe in North America. I can ask Ben about that. And they deal specifically in natural refrigerants, which I'm really enjoying and learning more about because the last, I think, 8 weeks, we've been talking about a lot of different CO2 applications from subcritical, transcritical, more on the technical side to technicians. But today we're going to be focusing more on talking towards consultants and engineers. And this is really, really important because I believe all sides of the industry need to kind of start learning about CO2 because it is here. And today we're going to have a great conversation. Ben, welcome to CO2 Mondays with Trevor. How you doing?
Pretty well, thank you.
Ben, why don't we start off and why don't you introduce yourself to the audience?
Sure. I've been working for Simco for the past 22 years, and prior to that, I was with Sabro for 8 years. And before that, I was with Docal, that was a pressure and heat exchanger manufacturer. And fresh out of school, I started with Enertrack, and I introduced the very first mini split Mitsubishi electric unit on the market.
Wow.
So that was this is my experience. I started like on the light commercial residential, then I moved to the semi-industrial, and then with Sabro, I was really industrial. And I discovered at that time that I was really a refrigeration guy, and I really got in love with ammonia system. And then when I moved to Simco, it was all the contracting part that was over and above all the knowledge I already learned with all those manufacturers. And I got really, really excited with everything I did and the all the opportunity I had to try a lot of things. And I would say beginning of 2008, 2009, 2010, I was hearing a lot of buzz. And I also went in Europe for the Chilventa show a couple of times. And CO2 was becoming something really, really like making a lot of noise, especially in Europe, not so much in North America. So I got really interested, really excited about that. So I went to the show 2, 3 times, and then I got in contact with very, very important suppliers of Simco and other people in the world. And some of them were Danfoss, Alfa Laval. Also went to see Green and Cool and Advancer.
Wow.
And I start my learning curve on CO2 by meeting all those people.
Yeah, and that's super smart because that's where it all started in Europe. And I know I've talked to many people about the late 90s, mid 90s, early 90s, and then by mid 2000s to it was in North America. And I believe it did come in through Quebec. And it's from all of you people like you going out to Europe and finding about this technology and bringing it back here, which is really cool, and bringing that knowledge back here because CO2 has been growing immensely in even the last 10 years. It has exploded and it's going to continue to grow. So what's your role right now at Simco?
I'm presently the Director of Business Development, and I've been in that position since 2012. Prior
Wow.
to that, I was a General Manager of Quebec Operation.
Awesome. So you would have lots of experience then in all sides of CO2. So let's just get right into it. For consultant and engineer, what are some of the things that you believe that we need to get the message out to them?
This is a simple but a very long answer for your question.
Yeah, I love it.
So the message I'm trying to carry, or I will try to carry today, is the following. When I started my research and when I start learning and playing with some of the tools and reading the material and talking with people, we are very used to see things in a very static picture. So you're designing a system. Let me backtrack. You start looking at your plan. You think about what you want to accomplish, what you want to do. Generally speaking, when we're talking about refrigeration, you need to calculate the load. you come up to a certain requirement, and then you start thinking about how am I going to achieve what the customer is expecting, and most of the time it's maintaining temperature for whichever you want to do, cold storage, pyro freezer, an ice rink, process, whatever. It's maintaining temperature and carrying the load from where you need to get it and remove it and bring it somewhere else. So starting from there, people has a very static picture, meaning this is the total load, this is what I need to design, this is what I'm trying to accomplish, and there we go. Make, equipment selection, calculate the electrical requirement, power requirement, motor size, pump size, and stuff like that. I would say that even myself at the beginning, I was only seeing this picture. And then I realized that generally speaking, when you do a traditional system, going with that picture, you have the right system and you're not too much in trouble if you're going that way. If you introduce CO2 in the picture and you do the same thing, it's great, it's wonderful. But then you're taking an instant picture of the worst case scenario. And now I'm going to diverge a little bit about the worst case scenario. And again, I went through that process myself. You look at CO2, you look at the pH diagram, you take any equipment manufacturer, compressor manufacturer software, and you start making selection, or you ask for selection. And you're getting back the selection and you're comparing a synthetic refrigerant compressor, you're looking at your ammonia compressor selection, and you're looking at the CO2 compressor selection, and you're going like, this does not make sense. It's like, how can people say that CO2 is an excellent refrigerant and I can achieve what I need to achieve when I look at the COP, EER, kilowatt per ton, name it the way you want to name it. At the end, it's all the same thing. And you're looking at it, again, a static picture, worst case scenario, and you're saying, doesn't make sense. And a lot of people are making this mistake.
Wow.
And they don't see the global picture, saying that, you know what, first, your system is not running 100% of the load all the time. Never does. So there's always a diversity factor. First thing. The second thing is your system will unload, for sure, which goes with the seasonal requirement, production requirement. By doing that, if you're going with a big traditional system, sometimes, how can I say that? Like adjusting to the load shift or load change when you have big system, big compressor, you can still do it, but your efficiency is not perfectly top notch.
Okay.
If you start thinking about CO2 transcritical system, and now I'm talking about CO2 transcritical system, you have smaller machine, smaller compressor, and you have a static picture of the worst case scenario. Then you start thinking about what's going to happen in March, what's going to happen in September, what's going to happen in November, what's in the middle of January, what's going on with my load, what's going on with my system, what's going on with my compressor. And that picture is not taking into account, I would say 90% of the time, when people are, the phrase I like the most, it's like, I'm trying to compare apple with apple.
Okay.
Well, guess what? The apple is growing all year round.
Yeah, exactly.
So this is part of the thinking that absolutely need to be part of the equation.
I like that.
And it's missing so many times.
This is something that goes back to maybe how we are taught to size equipment. Then so it's going even part, because that's how I talk to a lot of people. It is a static, just like you're saying. It's because I've looked into design, and I'm not a designer at all or an engineer, but it's always static like that. Why don't you talk about the way that you start to look at the picture and get it?
Yeah, okay. So to answer your question, let's put some numbers on the table just for the sake of discussion. So you have a cold storage you're making your load calculation and you're coming up with 100 ton of cold storage. Let's say a freezer that you
Mm-hmm.
want to maintain at 0 degree Fahrenheit.
Mm-hmm.
So whichever solution you're going to pick for that freezer, everybody should install a 100 ton system. Everybody should be doing that.
Mm-hmm.
If you don't do that, then it means that you're presuming that your diversity factor could allow you to install 70 ton or 80 ton. And this is a complete different debate.
Mm-hmm.
So we will presume right now that everybody's installing 100 ton system. And now you start making your equipment selection with a synthetic refrigerant, with an ammonia system, and with a CO2 system. And you start calculate the kilowatt of motor of every approach. So for sure, if you put it on paper for a 100-ton freezer, ammonia will be the least kilowatt or horsepower of compressor.
Yep.
Number two could be the synthetic refrigerant system. And the highest kilowatt or horsepower motor on the system will be the CO2 system, for sure.
Okay.
Now, if you look at your piece of paper, anybody will say, why am I going to install a CO2 system if the package or the equipment has the highest kilowatt? Why would I do that?
Well, regulations maybe.
Well, then you can ask yourself a lot of questions. Do I want to install a synthetic refrigerant system and change it again in 5, 10, 15 years? This is the first question you should answer yourself. Second question is, if I'm going with an ammonia system, do I believe that natural refrigerant is the best approach? Am I comfortable with ammonia? Am I equipped to work with ammonia? You answered those questions. And thirdly, if you're looking at CO2, is that a natural refrigerant? Yes. Am I comfortable to work with it? Yes, maybe not. You don't know. And finally, why should I install a CO2 system if on paper it seems to be the biggest amount of kilowatt? And this is where in the equation we need to bring, yes, you're right. But the first question you should ask yourself, where are you located?
Yeah, that's a good question because it all depends on where you're at in the world. If you're
Exactly.
Phoenix,
So
Arizona is going to be different than Montreal, Quebec.
exactly. So where are you located? This is the first question. The second question, what is your schedule of operation? Are you operating like 8 months, 9 months, or all year round? And if you are southern location, and I don't know if everybody has seen this map that was drawn by Danfoss many years ago, where you actually, the World War map, which is flat, and in the middle, there's a blue line, and Danfoss, and that was like 10 years ago, Danfoss was saying that anything above that, your CO2 system was more performant than anything below that blue line. And that was 10 years ago. Within those 10 years, there were so many things that were developed, discovered, tested, installed on CO2 systems. So I would think that this blue line that was just about in the middle is probably way more southern, right?
Oh, yeah.
So again, just coming back on your question, where are you located? How long are you working? And then can we have a global picture of all year-round production? So if you are located anywhere up north, which is like Canada, northern US, all these Scandinavian area, all those people don't even question themselves, because when they draw the entire picture throughout the year, even though you're installing the highest horsepower, guess what? At the end of the year, your energy consumption will be lower than anything else.
Yeah.
And people are saying, how is that so? Well, you're installing, as an example, a 6 compressor on a rack system. In the middle of July, it's 95 degrees outside, the 6 compressors are running. You walk in the same mechanical room in the middle of January, one compressor is running. And your load has not changed, your demand has not changed, but your power consumption is different.
Yeah.
And all that is because, and I've seen it a couple of times, for people which are familiar with CO2 system, there's the subcritical operation and there's the transcritical operation.
Mm-hmm.
And this is something that people, when they try to understand it, it's simple, but it is also so complicated. Because everybody understands that when you are within the curve, within the pH diagram,
Mm-hmm.
any type of system you're running subcritical, it's pretty simple, temperature, pressure related.
Yep.
As soon as you go above the curve, temperature and pressure, two different things.
Yeah.
And then everybody got mixed up.
Yeah, yeah, yeah. No, the first time I seen it, to be honest, and that's when I got back into pH diagrams. So as a technician, you don't really look at those. But when I do trainings now, that's one of the first things I do in all my trainings because it's so valuable, especially with CO2. And when I started seeing supercritical or transcritical, then compared to subcritical, I'm like, wow. And it makes so much more sense when you're looking at it and you think about it. I use them all the time in my trainings now.
I use it all the time too, but people being really comfortable and really understanding, just at looking at a pH diagram, it's not so obvious. Sometimes it's using words, sometimes it's using simulation, sometimes it's trying to play with compressor selection just to demonstrate to the designer, the consultant, the owner that, yes, you're right. In the middle of summertime, if you are downtown Toronto, your system will consume more energy that day.
Yeah.
How many days do you have like that? How many hours do you have in a year in those conditions?
Yeah.
How about the rest of the years? How about in the wintertime?
Yeah, no, exactly, and then when I seen those numbers too, it just boggled my mind because I was always taught that way. You size the system for the largest load, just like you said, but if it only runs that way 40 hours of the year, think about the amount of energy savings over that year. So that's very interesting. So have you noticed in, because I know you size and you worked on many CO2 systems, have you noticed a lot of systems being improperly designed or sized?
That's a very good question. I can hardly answer that. I don't see many other people installation.
Okay. Yep.
I mainly work with our own. Simco, we are very serious on our design. We never take risk. We
Yeah.
will probably install slightly bigger than too small. Generally, this is what we will see. Now, that being said, does the final operator owner is really setting up their system for the best operation? That I'm not sure.
Mm-hmm. That's a fair question because I've seen this many, many times where an OEM, a contractor, a consultant engineer would go in and they would size and design the system for the end user, but at the end of the day, the end user does not go with the recommendations by the contractor or the engineer. They get the system in and then that's it. The maintenance aren't happening, the updates aren't happening, the changes that need to be made may not be happening. So it's a very good point there.
Yeah. So you're opening a door that let's have a look, talking about the static picture in the middle of summertime, and I'm going in the middle of winter time, like January, worst case scenario, it's minus 20 outside. Maybe not in Toronto, but in Quebec, we can get that, believe me. So it's minus 20 outside. Uh, the system needs to run because it's a process. You still need a bit of cooling. And then you look at the system, and are you taking full advantage of the system? What's going on with your discharge pressure, discharge temperature? Are you still running transcritical, or do you take advantage of running subcritical at that moment? Because you could run subcritical.
Hmm.
Now, you heard that on many occasions, the top of the curve of the CO2 pH diagram is 88 degrees Fahrenheit.
Hmm.
So that means that if it's minus 20 outside, you can be below that point. So you take a standard transcritical compressor from any manufacturer, it's going to give you 15 ton with a 30 kilowatt motor when you're running in middle of summertime, and you take the same compressor and you run it subcritical in the middle of winter, it's twice the tonnage
Yeah.
and it's half the kilowatt.
I know that's so amazing. It's so amazing when I learned about low condensing and floating in. When you drop that down, you reduce that compression ratio. It's like, holy, you're getting all this capacity and less energy. I love it. I love it.
Exactly. So keeping that in mind, okay, that's nice. You have 6 compressor for the summertime. I can use 1 or 2 in the winter time. Wonderful. Now you add an extra layer, an extra step. We are highly promoting heat reclaim on every system.
Yeah, and that was something that I like about 4 or 5 years ago when I first started training on CO2. Had a buddy, and it was the middle of winter. It was so cold out here, and I'm like, "How's the rack running?" I think this was in Alberta, and he was like, "We're in transcritical right now." I'm like, "Transcritical? You should be in subcritical right now. It's so cold out." But what you're talking about here, heat reclaim, is very important depending on where you're at.
Exactly, exactly. So this is another aspect of CO2 that it takes a while to wrap your head around it.
Yeah,
Because you're going to say, once you understood the picture is dynamic in time, and you can have the lowest energy consumption by taking advantage of your outside condition. Now I'm talking about Toronto, but we're going to talk about other places
yeah,
just further down the line. Now let's focus on heat reclaim in Toronto, in Montreal, up north in Alaska, whatever. So now you have a debate, or you have 2 choices. I'm running my system subcritical and I'm paying the least electricity as possible. And then I'm using fossil fuel
hmm,
to warm up my area. And in today's world, if you want to do that, might not be the best, might not be the best approach. Or
yeah,
you can say, you know what, I'm going to force my system to work a little bit harder. I'm going to produce heat for the building. I'm going to cut my reduction of fossil fuel.
yeah,
And then it's a comparison between of how much kilowatt of electricity I'm paying more and how much gas am I saving. If
yeah,
you're if you're in Quebec and we have clean and renewable electricity, it makes sense. If you are in Halifax and your electricity is produced by coal,
yeah,
that's a different question.
yeah,
Saying that, we know that if we want to have decent heat reclaim with CO2 system, we cannot run subcritical. We have very little amount of heat when we're running subcritical.
yeah,
So I'm going to use the term condensing with CO2. And if you're below 88, very cold outside, and you're condensing at 55 degrees Fahrenheit, you don't get much heat reclaim out of that.
no,
So in order to do that, what do, you force your compressor to go up. You go over and above the curve. We end up in transcritical mode.
yeah,
And now we're producing heat. Now, this is where the complexity gets in line. And when I realized that, it was a real shock for me. Sometimes, on some occasions, if you're pushing the pressure higher, you're actually increasing your COP.
yeah. That's unbelievable. When I seen that, I couldn't comprehend it at first. I couldn't
Yeah,
comprehend. I'm pushing the pressure higher, but I'm getting better COP. Would you like? Can you explain that?
absolutely. Absolutely. Now, do you mind if I share my screen just for a
Here,
second?
let me just make sure you're able to share. Yeah, try it now.
I think it's important that we take like 5-10 minutes maybe just to share that. So everybody have seen those, and I'm sorry it's in French,
That's
but
okay.
this is like standard operation, and
Yep.
this is trench critical. So I want to bring you here. So this is a R744, a CO2 system like a normal pH diagram. So we can see we have evaporation, pressure,
Yep.
temperature equal. We have compression, sorry. We have
Yep.
condensation, pressure, temperature equal, and expansion, which is a normal subcritical cycle.
Yep.
And if you would do ammonia or synthetic refrigerant, it will be exactly the same thing. Now, where I want to bring you, there's a software which is called Simple CO2. I don't know if you heard about it,
Well, I'm
Trevor.
writing it down. I haven't heard about it, but it's great to know. I love learning about different software. So Simple CO2. Yeah.
It's for free. You can play with it, and you can see you have your CO2 pH diagram. You can set up some of the operating condition. This is in degrees Celsius, so you need to work with that. And you can see that I'm running subcritical here.
Mm-hmm. Yep.
But I have no heat because I'm a pretty low temperature. Actually, if you look at the, let me see, I'm looking, gas cooler is actually outlet, excuse me, high pressure. I'm running at barely 70 bar, which is very close to, I can't see it here, but it's pretty low. You can see that the top is 88, so I'm
Yep.
slightly lower. So I'm probably condensing, I would say at 60, 65.
Yeah. Something like that. It looks like.
So then we're going, let's push the pressure. So I'm going over and above the top of the curve. I'm in transcritical mode, and now I can provide heat.
Yeah.
Now the trick, why does COP increase when you're doing that? You can see here that during the winter time, my COP is 4.69 when I'm running subcritical. If I push it in the summertime, and I want to keep that very important, I push it in the summertime, my COP went down to 1.7. And this
Wow.
is why on paper, static picture, why should I buy a system like that?
Yeah.
Now, the whole trick is you see 0.4 here, which is the outlet of the gas cooler.
Yep.
If you push it further down left, your COP start going up.
Yes.
Now,
That
just in order to really see it live, and I know people are strictly listening.
is
Okay,
okay. Now we see it perfectly. Yep.
so simple CO2. So the only thing I'm going to do for people that could see the screen, 0.4 here, this is the outlet of the gas cooler.
Yeah.
Okay, so you can see that if I take that, it's very cold outside, and I let it go left. Look at what's happening with the
Wow.
COP. You see the COP right
Yeah.
here, right here?
Yep.
So and if you're in the summertime, you're gonna get out of the gas cooler right there.
Yep.
Your COP is there, and warmer you get, whoops, in Toronto,
Yeah.
you
She's just
know,
dropping that COP quickly.
I'm in Phoenix, Arizona. Oh,
Yeah.
here we go.
Yeah. 1.65 COP.
Here,
1.65. Yeah.
here you go. Now you get in the winter time, you still need the heat, but now you can get out very, very cold from the gas cooler, as cold as possible. Let's say I get out at 0. Look at the COP, what's happening.
Yeah. 4.16. That's huge.
Yeah, and then you can play with the pressure. And this is something else, which is, and when I was saying you look at COP, well, maybe it's a little bit too crazy now. So let's go back to 10 degree. COP is 3.71. And sometimes depending on the pressure where you put it, your COP at some point, you're getting to the most efficient COP when you get under transcritical, where it's going to revert.
Yep.
It's going to go down, and at some point, it's going up, and then it reversing. Why is that? Because the temperature curve are actually the red line here.
Yep.
And higher you get in pressure, you're going more on the left, more you're going on the left, less flash gas you create,
Yep.
more efficiency you're getting.
Exactly. So that's the big thing, right? It's because the less flash gas as you push that pressure up,
Yeah.
and
So exactly. So this is why when we are in warmer climate, and now I'm going to take just this little space to talk about warmer climate, that means that I'm stuck here, correct?
Yep.
I'm in warmer climate. I don't have the luxury of having snow in the winter. So when I don't have that luxury, I'm stuck here. I'm always stuck like that. Even in the winter, whatever, I'm always stuck that. So what do we do? So there's a lot of very bright, intelligent people that invent device that will improve that cycle and start handling this flash gas.
Yeah.
Now, I don't want to talk about ejector parallel compression, but this is what it's doing when we're getting in warmer climate.
Yeah. And that's what's so cool about CO2 and evolution over the last 10 years. I've been seeing all these different things from parallel compression and ejectors, all these different things, which is really good to see. And I know there's more things going to come. There's more things coming, which is cool.
Exactly. So now I just want to show you on the reclaim of the building. So if you are really close to the transcritical, but really close to the transcritical point, you're getting that much heat. If you crank up your pressure, look at the amount of heat you're getting. Now remember, those curve here, this is 140, this is 95. And I'm going back here, this is 140, this is 95. So you look at, if I'm really close here, you look at the amount of 140 I have available for the building, especially for potable water, cleanup, shower, CIP, stuff like that. I have almost nothing. If I push up my pressure, look at the amount of 140 I have available.
Yeah.
The rest available is still good for 95, which you could use in comfort building for heating and fan coil, radiant in-floor, stuff like that. So when you're using CO2 system, not only you have a really good performance, especially in colder climate, if you get that point as left as possible, but you can also work with decent heat reclaim in terms of temperature to actually supply two duty, one which is potable hot water, the other one that will be building comfort.
Yeah. And that's awesome. That's what I really like about CO2 because it's so versatile and you can use it very effectively in different applications in the same system. That's really, thank you very much for showing that. It really goes to show you that there is so much opportunity with CO2.
Absolutely, absolutely. Now talking about the the dynamic vision, I'm going to show you two other slides. So the famous chart that was used by Danfoss or was produced by Danfoss many years ago, this is the world map and you can see the blue line.
Yep.
And that was like 10, 15 years ago. And when I was talking about a static picture, you make your compressor selection, it gives you so much kilowatt per ton. But then after that, when you start playing with your selection software, you realize that colder your temperature is getting, better your COP is getting. So when I started in that business of CO2 10, 12 years ago, I was doing my own energy efficiency calculation that was based on bin data. So for people which are not used to the bin data, what it means is like you have the outside temperature and you have the number of hours that your location will be under those outside temperature. So since I had nothing to do at night, I was making compressor selection at various conditions, trying to see what was the kilowatt of that compressor, how many hours it was running, and I was trying to make an average COP for a dynamic picture, meaning from January 1st to December 31st. And then look at the COP. I was getting an average COP of 4.66.
Wow.
And when you make the static selection in the worst day of the year, you can have a COP of 1.6.
Yeah.
And this is what we need to explain to designer, people that will make a selection. Yes, you're right. The static picture don't look that great.
Yes.
But if you look at the entire picture throughout the whole year, this is why we can tell you that if you are selecting a CO2 system for your application, you're going to have 5% energy reduction, 10%, 15%, 30%, depending on where you're located and which option are you taking on your system. Now, somebody certainly mentioned adiabatic gas cooler as an example.
Yep.
So what is an adiabatic gas cooler? We're spraying water over the air-cooled condenser. Why do we do that? Because if you look at the bin data, there's maybe 45 hours that you're going to be in very extreme conditions. And instead of losing so much COP, well, we're going to spray a bit of water in your condenser and you're going to reduce your power consumption. You're using a bit of water, but it makes those very few hours not so bad compared to if you would not be spraying water.
Yeah.
In some places, you're saying, you know what, water costs me more money than electricity. Don't spray the condenser for 45 hours in that case.
Yeah.
It's always a question of having a global vision.
Yeah. No, and that makes so much sense. You got to think about where you're at, where you're locating, and the proper solution, because there's lots of different ones, and they're going to be different solutions for different locations on the planet, which is really good. And that's something that a lot of people need to understand. It's not one solution fits all locations.
Yeah. Now, let me show you something else. There's some software which are available in the market that actually calculate, instead of doing that like I was doing manually, you design your own system and it's going to calculate your energy consumption throughout the entire period of usage. Now you can see I'm only operating 8 months, and that will be typical of an ice rink in Canada, for example.
Hmm.
And you can see that your power consumption is changing throughout the course of the season. Now, if you look at this and you're comparing that to a synthetic refrigerant system, you can beat it by 15, 20% in northern climate. Now,
Wow.
if you look at a process system as an example, so I just simulate the system. I think it was a 100-ton system operating all year round with a freezer and the cold storage medium temperature. And I'm comparing it to a synthetic refrigerant. And you look at the profile, the blue will be the CO2 and the yellow will be the synthetic refrigerant. Well,
Hmm.
guess what? In the middle of July, look at the blue line where I am.
Yeah.
It's not a big surprise, but look at it in January and February as an example.
Yeah.
And if you look the global picture, well, guess what? At the end of the year, I'm going to be what I can see it because now I have everybody's face, but I think it's 5 or 10% less than synthetic
Yeah.
refrigerant.
8.9%. So that's still a huge amount of savings going head to head with synthetic.
Well, exactly. Exactly. So,
Yeah, that,
and if you're moving down south, there's other things we can do. You know, we can use an adiabatic gas cooler as an example. We can use ejector. We can use parallel
yeah.
compression, excuse me, and still keeping that in mind that it's a dynamic picture.
Yeah, and I like that because it is new to a lot of people. And a lot of people are used to sizing systems the way they've done it forever. But it's time to looking and thinking outside the box a bit and really get an understanding of it, because a lot of people need to see it just like you showed there, just see how it does. You just showed the numbers, the way it works. And then I like that the approach of a lot of people that I'm talking to are hesitant at first, but when they start to talk to more people about it, get a better understanding on how it's being used, because there's a lot of people that are still like worried about the pressures. But 410A has high pressures. 404 has pressures. They may not be as high, but they still have pressures. And it's inside of a system that should be like put together by quality technicians, and it's a sealed system with a lot of safeties. What's cool about CO2? There's so many safeties. It's no different in the industrial space. There's so many safeties to protect the people. So if it's installed properly, designed properly, installed properly, and serviced properly, you have no worries with any type of refrigerant.
Yeah, this is so true what you just mentioned. Safety of the worker, safety of the occupant, safety of the people around is always the very first thing which should come in mind.
Yeah.
But I don't want to make any joke, especially I don't want to make any joke about that. But when you look at what's happening on the market and some new refrigerant that's going to be classified as A2L
Hmm.
that will be slightly flammable, excuse me, whatever it's highly flammable of, slightly flammable, it is still flammable. Do you want like a small burn or a big burn? You don't want to get burned, correct? So it's
Yeah.
the same thing with it's to me, it's the same thing with pressure. If you're operating at 150 psi, if you're operating at 400 psi, or if you're operating at 1200 psi, your system should be designed and should be safe for that operating pressure.
Yeah.
And irrelevant which system, if you don't do your job properly, and if something is cracking, exploding, you're going to have damages. I wouldn't say irrelevant of the pressure, but we shouldn't say that, oh, this system is way safer because we're operating at lower pressure. Every system needs to be careful. Every system needs to have the right design, the right material, the right procedure, the right welding.
Yeah.
And because it's CO2, people are even more careful. We're using like stainless steel as an example on all the piping. Every wells will be TIG well, and procedure will be respected. Everything's going to be tested. Same thing as any other refrigeration
Yeah.
system.
And what I've been noticing and I liking about CO2, it's making people not cutting corners, but just forgetting about the way to do it properly. Just get, because you could get away with a lot of stuff with 404 or 22. Oh, I'm not going to pull a perfect evacuation. But people don't understand that 2, 3, 4 years down the road, that's compressor fails because of the day one install or something fails in the system. And with CO2, I think a lot of people are taking a bit more precaution, doing it right. No different than you would do it with a synthetic refrigerant. No different. It's just they're taking a little bit more time to do it the way they're supposed to do it, which I'm enjoying seeing because the more and more people that I talk to that install the CO2 system, they're like, oh, I'm doing a lot more proper practices compared to what I was doing when I was building a store with a synthetic. So I really like that.
Yeah. Yeah.
Why don't we talk about a little bit about some of the ice rinks? Do you have any ice rinks running on CO2?
Actually, we have over 60 something ring running on CO2 system.
Wow.
We have two type of approach. We have what we call a direct CO2 system and an indirect CO2 system.
Okay.
So briefly, on an indirect CO2 system, it's the same thing as any other refrigerant. You have a piece of equipment which is cooling down a medium, which could be brine, glycol, methanol, whatever that we are pumping through the floor. So that will be an indirect system. So if you have an existing indirect system and you want to replace it with a CO2 system, it's basically you're removing the other package, you put a brand new CO2 package, and you keep the floor as it is.
Okay.
And again, remember, you might need a bigger electrical entry because you have more horsepower.
Ah,
But remember, your energy bill at the end of the year, depending on where you're located, might certainly be lower. This is the first thing. The second thing, if you're building a brand new ring or you're renovating one and you're changing the floor, the best approach would be what we call a direct floor. So that means that we have no heat exchanger on the cold side. We are pumping CO2 directly into the floor. Why can we do that? Because CO2 is a dangerous gas, but could be higher in concentration in occupied space,
mm-hmm.
which you cannot do with ammonia as an example.
Yeah.
So I'm not saying it's not dangerous. I'm saying that we are allowed to have CO2 in occupied space as long as we respect the code.
Yeah.
And that allow us to do direct floor if the volume of the building is sufficient enough within the parameter that has been established by the codes and regulations. When you're doing that, and the best example are the speed oval that was done in Beijing for the Olympic, it's a CO2 direct system, meaning that they're pumping CO2 directly in the floor, and they went with 12 world speed records. Why is that? I need to take a couple of minutes to explain that, especially in an ice rink. when you're going with an indirect system, your ice rink is 200 feet long, correct?
Yep.
And normally you want to maintain your ice at 20, 22 degrees Fahrenheit. In order to do so, you're going to be pumping glycol, as an example, in the pipe underneath the slab. In the pipe, you're going to be pumping glycol at 16 degrees. And then you're going throughout the length of the rink, and you're going 16, 16.1. In the middle, you're 16.5,
Yep.
17 at the end. You're coming back 17.5. You end up at 18. So you have a change in temperature because you're going with sensible heat,
Yep.
and your glycol is going to change in temperature. And in order to produce 16-degree glycol, your compressor needs to work at a suction at 5 degrees because you have 10-degree TD into your evaporator.
Yep.
So to have 20-degree ice, we need 16-degree glycol, 5-degree suction. If you're going directly with CO2, no evaporator, you're sending 18 degrees CO2, 18, 18, 18, 18, 18, turning at the end, 18, 18, 18, 18, going directly to your compressor.
Wow.
You barely have no loss in the pipe. Your compressor is running at 17.5. So
Wow.
how can you compare a compressor running at 5 versus a compressor running at 17.5?
Yeah.
First thing, then your ice temperature, 18, 18, 18 all the way along. So that means your ice temperature is even everywhere.
Yeah.
And thirdly, the pump, when you're trying to pump glycol through the floor, you're going to have a 15 kilowatt, 20 kilowatt pump. When you're pushing CO2 through that floor, you're going to have a 2 kilowatt pump. So if you add all this, then you end up that we did a nice rink in Montreal, Concordia University, that we changed from an ammonia system to a CO2 direct floor. And within the very first 5 months of operation, they saved 300,000 kilowatt hour.
Wow. That's so impressive.
And
That's
this
so
is
impressive.
not even talking about the ice quality.
That is awesome. And it's like things like this, solutions like this that really make me excited about refrigeration. Because I didn't even know about this last story you just said. I did hear about the Beijing Olympics, but I love hearing that because this is the opportunity that CO2 has, and it's very fun to learn new stories and find out more about it because I really want to learn a lot more.
I don't want to interrupt you, but if I can just springboard from that, what we just experienced with an ice rink, you can do the same thing with a cold storage.
Wow.
So think about it. You have an existing ammonia plant, and people are getting a little bit more nervous about having ammonia in an occupied space. So you're doing exactly the same thing as an ice rink. You have an ammonia plant, you're cooling down glycol, and you're pushing glycol into the cold storage. Now we have the same thing. We need to run compressor lower. We have an heat exchanger. We have a pump. So we're spending more money than sending ammonia directly. Now there's a place in the middle that instead of doing that, we can just use the ammonia to cool down CO2, and we're pumping CO2 through the coil, through the evaporator in the cold storage place. So it's pretty safe, highly efficient. Your pump is very small. You're not changing temperature as glycol, and you have a very clean circuit because you only have a CO2 circuit, no oil, no compressor, nothing. Pretty safe, highly efficient.
Yeah.
And this
Yeah.
is so simple. This is so simple to do. You would be impressed, Trevor. If you would see an installation like that, it's marvelous. It's
Well, I can't
running.
wait to go to an installation with you and see one. So we'll do that. We'll do that for sure.
And we call that a CO2 brine system.
Hmm. Worked on a couple of those, and that's one of the things I did notice when I was a technician. I worked on glycol system that was using propylene glycol, and then when I worked on the CO2 pump system or secondary system, the pumps were smaller. Moving that. So that was something that I did notice as a technician.
Exactly. And the only thing left would be the defrost of those evaporator if you're running on low temperature. And there's two easy way to do that. Electrical defrost is mainly how they do it in Europe. In North America, we're going to use up glycol defrost on those evaporator, which are connected to the heat reclaim system. So not only you're doing defrost for your evaporator, you can provide heating for your building. You can provide in-floor radiant heat for, for some area. And even people which are tired of shoveling or snow blowing where the, when you have a cold storage and you see so many trucks going in and out, backing up and everything, you put a bit of pipe under the asphalt, you circulate warm glycol right there, snow blowing is finished. It's over.
Yeah. And I love, that's what I love about learning more about CO2. There's so many different angles, and it's just we need to get more of these messages out there so people understand the value of it. I wanna thank you, Ben, so much for offering a bit of your knowledge, because I know we could go for a couple more hours. Just I love these conversations, but well, let's get into some questions. See if anyone has any question. There is one in the chat. We've got about 8 minutes left, but one of the questions from Dimitrios: when you move the gas cooler outlet temp, I'm assuming this is from the software. When you move the gas cooler outlet temperature, I think superheat changed too. Is it the loss on suction line that changes that superheat? So when you move the gas cooler outlet temperature, it changes.
I'm not sure I perfectly understand the question, but from what I can read, superheat is one thing that you want to create at the inlet of the compressor. If you don't have a good superheat at the inlet of a CO2 compressor, you might have issues with oil. I'm sure a lot of people already talk about that. So creating enough superheat at the inlet of the compressor is crucial. Now, if your outlet of the gas cooler is something which is completely independent of your superheat at the inlet of the compressor.
Yeah.
Now, we can go further in talking about isentropic efficiency of your compressor, but I don't want to go there.
Yeah, I know it'll be another couple hours. I do, but we got to be cognizant of time. So yeah, he just meant on the software. He notices that the superheat changed on the software. So
yeah, well, sometimes the software take into account that you have a liquid suction heat exchanger. So you can cool down or you can subcool the outlet of your CO2 from the gas cooler. So you subcool it by creating superheat at the entrance of your compressor. So that's one way of doing it. And then you can play with the efficiency of that heat exchanger. So maybe this is answering the question.
No, awesome.
This is why it's doing that.
If anybody, that's great, Ben. Thank you. If anybody wants to unmute and ask a question, they're more than welcome to do right now, or you can put it in the chat for Ben, because this is the opportunity right now. We have the expert here. We have the guy who has the knowledge. He traveled the world. He worked at all these, went to all these manufacturers to learn this. This is the time to ask the questions. Ben, where can people get a hold of you or your company if they want to learn more about you and what you guys do?
Well, it's pretty simple. You can go on the Simple Refrigeration site. We have tons of marketing material there, very interesting material that people could get. Most of our credentials, most of our information are on our site. I am on LinkedIn as well, so you can find me, Benoit Roddy, under Simple Refrigeration. Get my information, send me a message, and I'll reply to you.
Awesome. Awesome. I want to thank you so much. Anybody have any questions?
Yeah, I have a question. My question is with respect to the technology of this CO2 refrigeration. As in our DX refrigeration system, we have got a standard components and a standard cycle. And what I understand, CO2 is still evolving in terms of types of the design. Already we have subcritical, transcritical, and under them we are having what I learned like from Bitzer is developing or Carrier is developing. In some different 7 types of different CO2 systems are available. So it feels to me that we are still evolving into the CO2 refrigeration. I belong to India, where the temperatures are normally hot. We go as high as around 45 degree ambient. So here, I just want to know which system could be more beneficial for us as a evolving, as I understand when we say the CO2 refrigeration systems are evolving, which could be the better option. I would like to know about it.
Yeah, that's a really good question, and I can only partially answer it because I'm not a manufacturer and I don't design entire rack system. Let's put it that way. But there's one thing I can tell you, that one of the biggest growth in the market that we see right now is in Australia and South Africa, which are probably comparable to your location in terms of outdoor temperature. Now, continuous developments are being put on the market. There's tons of research and R&D being done. There's a lot of people that do tests on brand new approach. I know two things work for a warmer climate are parallel compression. I didn't talk about it, but a lot of people probably already
Yep.
talked about it. And of course, ejector. An ejector could be used on many places, on the low side, on the high side. I'm not an expert at that, but I know that a lot of manufacturers are working really, really hard to make CO2 transcritical system very, very interesting for much warmer climate. For me, I guess I'm lucky because in the wintertime, I got a shovel, but at the same time, a CO2 system is a no-brainer in our climate.
Yeah. And I even
Okay,
have
thank
friends. I've
you.
done lots of talks, and I got friends, and I think Andre is on here in South Africa. They've been doing it, installing for 11, 12 years in South Africa, and he's saying like they're running at 45 Celsius, perfectly fine, their
Yeah.
equipment. So
And I've seen on LinkedIn recently also a publication that was stating that one of the very first supermarket in Saudi Arabia got a CO2 system installed down there.
mm. So that's a
Okay,
little
thank you.
that's just a little bit of research you have to do, but like Ben said, there is lots of technology, and we did one. I did one with Andre Patno to talk about that. So if you go to my YouTube channel, there's one on high ambient strategies. So that's one to take a look for because there's a lot of them out there.
Absolutely.
Any other
Okay.
questions? Well, Ben, I want to thank you so much for taking the time. This was awesome. I hope we can do this again, and I'm going to take you up on that offer that I said that I'll come and visit a site with you at some point because I love learning. I love seeing this stuff in action, and I can't wait to see everyone at the next CO2 Monday with Trevor. Thank you, Ben.
Thank you.